Okay, so if you see my my screen, this morning we with climate, and in my here I had tectonics, climate, and autogenic. And so tectonic climate, I should say tectonic signals, signals, and autogenic signals. So I drew those little sketches for autogenals, and we spoke a little bit about it. In a way, it's by opposition to allogenic, A-L-L-O-genic. So genic means origin, and allo means an origin of the signal, which is outside of the system we are looking. For instance, water discharge coming from the source into a river segment, or sea level, changing the profile of a river. These are factors that I primarily they outside of them. I am looking at as a stratigrapher, for instance. And autogenic is also internal dynamics, because that is the result of the internal dynamics of the system. And you can think of it this way. So I'm going to go through 1 and then 2, and perhaps there is no 3, but then I will go to here. Just a little rotating wheel with some little dents here, rated length L. And you know, it's one of those, sometimes there are toys like this that go click, click, click when you turn. This is trivial, okay? But I think this is how I see those systems, is that if you see something that makes a signal, and even if you turn the wheel with your hand or with an engine, with a motor, even if you turn it at a continuous rate, there is something in the system, in this case, the teeth here, and this device here, which is like a little thin plate of metal, for instance, that is going to create a signal that is itself episodic, okay? And so if you look with time, what happens? The rotation rate, but this little piece of metal here that is fixed here and that can be moved by the dents is going to go between position 0 and position 1 and then click, and you go, you increase, you change the position. So the rotation rate, you're gonna have a sound coming out of the system, which is episodic and which is a signal. I don't know if that's clear, if everybody sees what I mean here. And to some extent, you know, period of this signal is going to be somehow related with the distance separating the dents, the teeth. So for instance, say I have 2 of those teeth instead of 4, and I rotate 1 round per minute, my click is going to happen twice less often than if I have 4 teeth. So the distance is important for a given rate. The rate important for distance. So the time here, it's always the same relationship as the little calculations that we have done with flux or with distance and with rates. Time is distance here divided by rate. So there is a typical distance, a typical length scale in this, a typical time scale, and a rate. Okay. Here in the second, from that little drawing to a much more something closer to reality, but still very, very conceptual, is it's from, oh, sorry, not a mountain, just a hill seen from the side, a cross-section through valley floor, and then another valley floor. What we know is that there can be uplift, and what we know from nature is that you go over a certain slope, you can trigger landsliding. And usually what happens is that you pushing the rocks up, increasing the slopes, and you have to exceed the slope to trigger the landslide. And it's not that you exceed it just by 1 millimeter, for instance. So you let's say threshold slope, let's say 85 degrees, for instance, or 30 degrees. Sometimes it can be stable up to 40 for some reason. And some okay, it's like avalanches when you're skiing. Everything looks fine. The slope is covered with snow, but this slope actually 50 degrees. When a skier goes on it, then the avalanche is triggered. So what happens is that you increase slope and it goes back also much more down to a lower slope. So you constantly oscillate between and below threshold, above threshold and below threshold. And it's exactly like this little rate of here, going from position 1 to position 0, 1 and 0. And the result of that is that this process here, even with a constant uplift, let's say this is a wrong, this oblique is compared with time. This is time, and this is a vertical axis on which the horizontal line is constant uplift. And I am measuring flux here at the exit of my system, at the outlet, bottom of. When I have a landslide, I get boom, a big QS, and then I get periods without any flux. Okay, 0, and then boom, another landslide, and then 0, and then boom. Okay, and to some extent, I could think about a very similar for the period of landsliding. Is going to be the distance that needs to be exceeded. So there is a typical depth of landsliding. It's this typical depth of landsliding in this mountain range. It depends on lithology, it depends on many things. Divided at which I go over the threshold, that is going to somehow govern the time scale between landslides. Okay, so now we go from this pseudo sketch. Is this clear? Don't hesitate to ask questions. And in terms of quality or functioning.
One question, but yeah. What do you see? It doesn't. I mean, the time in which every landslide occurs is not the same because that's what you said, depending on what triggers.
It could be periodical if you if you would make a numeric, I think it could be periodical if U is very constant and if the depth of landsliding is if you leave a little bit of freedom to the system, it's going to be you will not have an exact in nature. It's not going to be exactly periodical, but you can always think about a typical recurrence time. We often say characteristic time or typical time in the system. Okay, that is, it's, you visualize nature, everything is often different, but you have a typical uplift rate in a region, you have a typical depth of landsliding, and therefore you can have typical for the land recurrence. and it's region specific, context specific. Okay, now over setting, and that's a view, a plan view of a system. Here first fully theoretical, and here something that looks a bit more like reality. Just a view from above of a channel, bringing sediment into an area here. So from confined flow to unconfined. Okay, as a thought experiment, think about water element, and so here I have T1, T2, and T3. What can happen conceptually is that you bring sediment as you go unconfined, from confined to unconfined, you drop your load of sediment here in this little accumulation time. Or once you have dropped sediment here, next time you bring water and sediment, here's a little, you're gonna deposit either here or here. So what will happen is that, let's say for some reason you deposit at 2 here, and then at time 3, when you have sediment here and here, at time 3 you are going to deposit here. Okay, if I do a section, this is the accumulation 1 at this section. It's a little bit like a bump. This is accumulation 2, and this accumulation, and these are called compensation. This is the process of compensation. Why? Because you compensate, and basically you just built a strata into an alluvial fan. Next time you will probably deposit here, and then you probably compensate the topography. Okay, and so you can see that as oscillates and then you're going to go T1, T2, T3, T1, T2, T3, exactly in a click manner, like here, or like a continuous flow, yet your accumulation will go sidewards to the left and to the right and to the left and to the right. Typical time scale here of this compensation, the time scale of compensation and lobe switching, you could also see you need a time, and you have a rate, and you have accumulation. So you again need to have a distance, a typical length in your system divided typical. And so the typical length scale that governs that is the height of a typical accumulation. Okay, and then the rate of sediment, or the rate of sedimentation. Yeah, the rate than the flux. So all in all, you get a time scale here that is called the time scale compensation. And I've said a word to this when the other day we discussed already, we pre-discussed autogenic. Here, delta, that could be something like the Rhone delta, for instance. Main channel, and this channel divides into several channels, and basically the question is, all of this is theoretical here, and we've discussed that. How is this going to work? Okay, what is the time scale of compensation in nature? How long does it take for this signal to be expressed? And Wang and Kyle Straub and others, Hayek, Elizabeth, they've done exactly those experiments in the lab, and then to deltas, and they come to this expression that the typical time scale of compensation is h channel depth divided, can be approximated in terms of dimensions as h, the channel depth, divided by the rate of sedimentation. And so for a system with h equal 1 meter and s equal 1 millimeter per year, we would have TC time scale of compensation of 1,000 years. And for the Mississippi, as we already discussed, with channel depth of 30 meters and a subsidence rate of 0.26 is to sedimentation rate in this case, we have a TC, the time scale of compensation, the compensation time scale of 115 years. So there is a click signal in this delta with that frequency, with that period. Now the question, as we already discussed, is this signal is going to be expressed in stratigraphy. We've already seen this morning that there is a signal here in climate and in the astronomy. Okay, will this climatic signal be stronger than the signal? That's the question. And we don't really know. Another way to see this is also more vocabulary. I really like this paper by those physicists here in Nature in 1996, studied the avalanche dynamics in a pile of rice. And you see a close-up picture of a topographic profile of the pile of rice. So you have rice in this drawing here. You have rice coming here. Elisabeth, excuse-moi, je suis en cours. Je peux te je me suis dit que... désolé, non, j'ai pas changé le statut. À tout à l'heure. Rappelle-moi. Ouais. So rice coming down here at a constant flux, and it builds a kind of a rice pile. And when it is the out, okay, you can do that at home, but you're gonna have rice everywhere. This happens time we do home anyway. So you can do that, and you can study in detail the dynamics of this. What was interesting for the physicists is how what slope do you reach, how do you reach a certain slope, and what really happens in the system. And so they coined the term self-organized quality, because you see the rice grains are actually quite well oriented. They have an orientation, non-random, and what happens is that they kind of imbricate into each other, and sometimes build slow are unstable, but that exists a bit like in nature. You go to some cliff and you wonder, why is this not collapsing? It's exactly that in a little microscopic person, you will be there on that grain of rice here, looking at that slope and say, "Oof, this is going to fall onto me." So directly that, and at some point they collapse. And when they collapse, so this is this slope here. When they collapse, that's a system. So you have some sort of avalanche dynamics. And this is the result, with time and the flux of both piles in a very non-constant output with some sort of time scale. I fear the worst. Yeah. Here we can see nicely a rice pile and sometimes, but over rice, it looks like an organized system because the slope is relatively constant. So we can think of it as a nicely organized pile of rice. If you take a snapshot at any moment, the rice grain is always trying to reach the same slope. Yet sometimes there are critical events bringing the grains down. Okay, stop. And now this is what I in 100 kilo years, and here is probably a video on my computer. Yeah. little we did in Minnesota in the laboratory of Chris Paula, and here we used, you know, this isolated foam construction, the pink foam, and what we built was valley. So you have a slab of that foam. It's about it's all in inches. I don't remember. It's about 3 or 4 centimeters. We superpose this knife. We stick together with tape 2 pieces of it, and then we did a nice level. Okay, that's a big basin that you can control sea level. And what we did is to see is we bring sediment from above. The sediment is transferred downstream. It builds a delta here that will be a low stand delta out of Thais Valley, and we rise sea level, and we see how the valley gets filled. We've published with Rennes on that, so you can check that on the web. But here I just there's sound. Here, sorry, here you've seen the setting. I don't know if it's enough. Do you see my? Okay, so let me just make a pause. Yeah, here you see it's all dark because it's a mixture of sand and coal. You see how rudimentary it is. We stuck the stuff together. I mean, it's not ideal, but and we put preliminary experiment just to test things. So here we bring sediment at a constant rate. So we have an alluvial fan here. This alluvial gives sediment to the valley, which has a certain shape, and this sediment and coal are down the area, and here is the delta. And let's say yeah, what I like is that we see the dynamics that we were speaking about, is that you deposit the sound in one place, and deposition here drives, so you get those offsets and those divergences outside of this. You also see 90 plumes of suspended load. But you see how the system is building itself. It's more like an alluvial fan. What's the term for an alluvial fan in the sea? Delta. So, but you see the dynamic of it. This is very extreme. I have many more experiments, and they are fascinating to look at. But this is the dynamics of compensation. Here it's actually quite stable, but excellent. Well, we've built this big one in the middle, but sometimes it is the whole integrated dynamics of it is this compensational stacking. Okay. Question, switch to another chapter. I will start, and so perhaps you are there already with Jean. I will start with now. Now we want to come back to the idea of a sedimentary system, of a source to sink system, and to discuss how. And so there's a little bit of theory again, and we're gonna do a one thought experiment afterwards. But just to illustrate what Francois already explained, but sedimentary systems, source to sediment routing systems, They can be at all scales, but they increase himas, which is an uplifting area with a lot of relief. There is a deep root for bringing sediment to the surface and for erosion. Then often you have a zone with more low, because this is a zone with sedimentation at the bottom of the mountain with subsidence, and so this zone is mostly your final sink, which is the marine environment with a large delta. In this case, the Gange Brahmaputra delta. Okay, and one of the, so we've just seen that there is autogenic variation. Those, so here, if you are a stratigrapher, you have a core in this delta, and you see what's explained, deepening, shallowing upward cycles. You wonder these shallowing upward cycles due to sea level cycles, like orbital cyclicity, 20, 40, 100,000 years driven by climate, are autogenic, like we just discussed, or could they be due to also orbit cycles, climate, that would act in the mountain range, and by changing precipitation and temperature, cycles and variations of sediment flux over those periods of 20, 40, 100,000 years. You could see suddenly a conglomerate here. Can this be due to earthquakes here, or a sudden change giving more sediment and then bringing more sediment here? So every change in stratigraphy, every change in sedimentology in niches that have in your delta, you would like to be able to associate it with either a change in the basin or a change of the basin in the source area. If we want to understand how source areas work, we need to be able to read the stratigraphic. Of course, you can imagine, for instance, that if you make a thought experiment and you bring with trucks, you bring tons and tons, but you bring 100 trucks of gravel and drop them in one day here in the Brahmaputra. So let's say that makes a nice big 100 meters high mountain of gravel. You wait here, or you ask friend and you have a phone and you ask them, what do you see coming? Here, of course, gravel are going to be diffused along the system, and perhaps you'll need to wait 30 years before you have first that year. If you could mark them, how long does it take for gravels to come here? And are they gonna, are all gravel put together and then go further, pass like a wave? Or are they gonna come the first one in 30 years and then the slow one in 20 years? Okay. So this is what, this is one of the questions, is how such signals are transferred to the sedimentary system. And we need to know that, because if we want to understand tectonics and climatic influence on landscape evolution, to look at graphic records in the foreland close to the mountain. If we want to understand how sea level has an impact on coastal systems, perhaps in such them, but we are still too close to mountain influence. Okay, so all of this understanding should allow us to decide where we should investigate the stratigraphic record to understand the Earth history of climate and tectonic variation. And I've drawn something that I should come back after I did the rest. I'm looking at time. I don't want to I would like to do two, at least those two slides. equilibrium, and this one also on characteristic equilibrium time. So I hope I do it in the right way, and but I decided to start with this one. Here I am at a slope. So this is elevation and this is distance, and I'm looking at the slope here. Then it could be 100 meters high, for instance. Culling measured the flux of slopes. He measured QS, and he related it to alpha, the slope of marked that the flux at the bottom of a slope is actually proportional to the slope. Okay, if you have a steep slope, you have flux out of it. If you have a gentle slope, you have much less sediment. And he said that QS is proportional times dz over dx, because dz over dx is actually the slope. Okay, this K here is the diffusivity or the efficiency of the sediment transport processes. Because different lithologies, as we've discussed with the stream power law, it's something that is it's not a K, also a constant of proportionality that determines the slope. So in certain climate, certain slopes will give more sediment than other climates. With certain slopes will give different sediment supply than others. Okay, so the K is to fix the proportionality between slope and sediment flux out of it. Do you agree with this? If you make a thumbs up,
yes.
I'm happy.
Yeah.
Okay. My is about topographic evolution, and I'm going to use that, but here it's this is the bottom. It's just it's somewhere on the landscape. Okay, the pixel or a cell of a grid, of a numerical grid. What I want is how of this cell evolves with time. Okay, and let's say I'm in a basin. I'm in a sedimentary basin. I could, if I look at a certain place, if I have a certain flux of sediment coming in, a certain quantity of coming in, and a certain quantity of sediment going out, I can just say that the elevation here changes as the balance between what comes in and what comes out. Very simply, if I bring 10 and 8 is going out, it means I stored 2, and if I have just deposited here. Okay, so the change in elevation here is dz over d, to be mistaken with slope, which is dz over dx. It's just a spatial thing, whereas here is a variation of the elevation with time. The variation of elevation time is the variation of flux in space, because it's qs in minus q out over this distance. Do you follow me? That the change in elevation is the influx over that place. Okay, so dz over dt equals dqs over dx, and you just use in this equation 2, if you replace qs by that, because this can be applied to a wide range of setting and not only hill slope. End up with an equation that perhaps you've discussed already with Jean, but you end up with dz over dt equals k times d the double derivative of z divided by dx squared. Okay, and this is apparently a differential equation. It's not my, but this is an equation in which you can describe the elevation of the land with time as a function of diffusivity and the slope on the landscape. And what you can do with that is a non-dimensionalization. I don't know if the orthograph is correct, but you can replace every single one of these variables with the variable of your landscape. And for instance, at the scale of a mountain range, this is something that was done, at least I read and understood from a paper by Chris Paola in 1992, but it's made in many, many other papers. But so that we let's assume all of these two equations are enough to want to know what's the typical time scale of response of my landscape. What I can do is non-dimensional, and to do that, I can replace every single one of those variables with a typical variable. So Z will be the height of the mountain range. Let's call it big H. Time can be replaced with typical time, characteristic time of evolution in my landscape. And X in my landscape, big L. I just replace, so I have H divided by L equals K is coherent to my landscape. So we don't really have it's all there. I end up with H here because here Z is derived twice, whereas here X is squared. So I have H squared. And so I have this equation which just simplifies into typical time scale equals L squared divided by T. And that, I think, very interesting, and there are other ways we can find it. If we have time, I can show you how to find it. Dimension of K in meter square per units of time, because this is in meter square. And so that relationship in a diffusive system, typically we will have characteristic response time, equilibrium time, proposed L square, the typical dimension of the domain squared, and diffusivity, efficiency. And if I have time, I would like to give you more of a feeling for that with these drawings. Here, what I've drawn. So there is, we first look at this first part of the drawing, and then there is a line. And then, so in this first half of the drawing, I just did what I represent is a metallic bar, which is actually continuous, but it's a metallic bar. L equal 1 meter here, segment meter. I have a thermometer to measure temperature, and I have another thermometer at the other end to measure temperature. And so in all the length of my metallic bar, my metallic rod is 2 meters. And here I have a heat source, just a light, to light a cigarette, for instance. And this is a very thin bar. What I can do as an experiment as a thought experiment is I can start lighting my lighter at time T1, let's say. So I am in room temperature until T, and I suddenly, I don't know what's the temperature of a flame, but I don't know, I would say 1,000 degrees or less. So I just start my light here and put on. Okay, so Here my heat source, that's how temperature looks like here at the source. Okay, so here at the source, I have an increase in temperature at time 1, instantaneous. Here I have a thermometer. What do I measure 1 meter away from my heat source? I probably measure something like this, the black part. Temperature increases, it is the same temperature as the source. So in red is my signal at the source, in black it's response at the sink, at least where I measure it. Okay. Each equilibrium temperature is Tec, is the equilibrium time to reach the temperature that is the time for me to feel the temperature that is imposed at this end. Okay, and this Tec is proportional to square divided by the diffusivity. Imagine you have a imagine you have a superconductor. When you put your heat source, instantaneously you reach the temperature here afterward. Okay, so you burn your finger if that's somebody holding the rod here. So on a superconductor, or supernova, we say, activity is very high. Okay, Tec is close to 0. You divide the length by something very big, Tec is close to 0. If, however, I have something very isolating, insulating, then K is very small. I divide 1 meter divided by something very small, and it takes ages to reach the temperature of equilibrium. Now, just to follow that, let's say I measure temperature here at the other end, okay, after 2 meters. How my response looks like. It's not just twice longer. It doesn't take just twice longer, because the bar is, but this is L square, so it takes 4 times more time to reach. Let's say here was 10 minutes before I reach equilibrium. Here it's going to be 40 minutes. Okay, just because of the square here on the length. So that's also important, because the length of a transverse is going to be phenomenal. An increase in length will really play a big role in increase the rest time of the system. Okay, the equilibrium time of the system.
Sebastian,
yes,
one small question.
Yeah.
Thinking in the way that you arrive at that equation,
Do
different parts of the basin have different K values, or?
So here I have a metallic bar, and its diffusivity constant. But let's say this metallic bar is a river, and this is the heat is set supply. Okay, this works if I just bring sediment and I change nothing to the river. Okay, the diffusivity is constant. But as we said before, those parameters often are not independent. And let's say I have a climate change as DTM, where I increase temperature and discharge. If I increase discharge, what do you think about K? Is it going to decrease? Okay. If I increase discharge, am I going to increase? Am I going to increase diffusivity or decrease diffusivity?
I would say increase.
Yes, because I will increase the efficiency of the system. Therefore, I will decrease response time. Okay. On the I go to climate, on average, I will decrease diffusivity. So the complexity here, and that's something that Jean has worked, is that during climate cycles, you also change not only you change, you have a signal in the source, but the signal actually modifies the system itself. So it also modifies the diffusivity and the response. So this, the scale of climate becoming warmer in the early Eocene, and we see the hyperthermal, and then climate becomes cooler, and we don't see hyperthermals anymore. Is it because the sensitivity of the system increases warm and then decreases during cooling? So this is the kind of complexity that's going to come and adds on top of that.
Okay.
So to follow up on that, Lucas, that's a bigger than the one that I have here. But we speak often about the timescale of the perturbation with respect to time of the system. So if I go back to here, my first experiment, I did a change in heat here at the source. You can see that I need to keep my lighter on for at least duration of equilibrium time for the signal to be felt. If I increase, put my 1 minute, and then I stop the lighter, and I know from previous experiment that the equilibrium time minutes. Then if I stop after 1 minute, then and I have my thermometer here, I'm not gonna record an increase to equilibrium temperature. Okay, so let's call it the perturbation period here. The duration for which is the TP. It's the period of perturbation, the time of perturbation. If it's smaller than the equilibrium for the system, then I will only see a response that is buffered, that is different from the signal. So if I add change to high temperature, light on, keep it 1 minute, then lighter is off, and then again on for 1 minute, and then I do that again, those perturbations for long enough, then I will see progressively increasing, but my response will not look like my signal. Okay, very important, because my system is diffusing and is altering, modifying, obliterating, obfuscating, all the synonyms you can find. It's changing. It's in the sync. Basically, we do not see the same as signal. So stratigraphy, it's important because we would like to be able to interpret, to say the right story about the source. We read the stratigraphic record. Now, if the timing of perturbation is sufficiently long, with T, say I keep my lighter on for 40 minutes, and my TX after 1 meter is 10, then I really feel my perturbation. My runes look like my perturbation. Here, if I zoom in, I will see that. So I have 10 minutes of response time, but signal lasts for 50 minutes or 1 hour or more, then I see a very close resemblance, and response time becomes negligible with respect to the duration of the signal. So in the stratigraphic, I see that, and I get the signal. Okay, so this is I think that's it for characteristics. Just I don't know if this is clear, but I think this is fundamental because it's the relationship between response and signal into what type of system in nature. As you already pointed out, things are much more complicated because diffusivity evolves, etc., etc. But to address what you see in stratigraphy. I have some potential application of this to a project. And again, there is three parts. What I'm looking at here is, again, a phrenologen. This time is not just a hill slope, but it's an entire mountain. So you go from the foreland, and then you have the mountain range. It's symmetrical. I have compression, and so this compression drives tectonic uplift, and I have erosion. Okay, the question always is, how long does it take to reach steady state? What's the characteristic equilibrium time to reach steady state? And so let's say I suddenly increase compression. So this is steady state 1, and this is period 2. I increase compression, I increase uplift. At the beginning, my erosion is not enough to compensate and my growth. The question is, how long does it take to reach steady state again? And so how long does it take until you have the right capacity and the right magnitude to balance tectonic uplift such that I reach a new steady state? If you see that in terms of elevation with time, I have steady state 1. I draw, a blue is a lead wavy because, as we said before, let's imagine steady state is not, it's approximately steady state. It's absolutely constant. And here I multiply by 2. Elevation will increase, okay, during this time when erosion is smaller than, at some point I will reach a new steady state at which erosion is equal to uplift. Okay, and here Paleocene, 55 million years, and Eocene. Why? Because in the Pyrenees we have such a situation, or we have let's assume we have this situation just for the pragmatic use of the didactic use of. We can discuss a lot about the reality of it, but on this diagram here I have put maximum topography, and here I have put time. Okay, this is a paper that is currently writing with Louis, but Gail also, Luis are into this. What isn't it? But one of them, the main one, I think, is what we think is the evolution of topography in the Pyrenees with time. So we see an increase in topography during the Cretaceous and Paleocene, and then we see a fast increase of topography in the early Eocene. Then some sort of steady state, in the sense, maybe it's not a steady state, but some sort of stasis or topography during the Lutetia, Bartonian, and reaching the Priabonian, and then at the end of the Eocene until some sort of maximum at the end of the Oligocene, and then slowly decreasing. Okay, that's with thick glasses with no detail. Okay, so that's if you're almost blind, but it's about motion we see of the Pyrenees. And if you look in detail, it's probably much more complicated, and there should be a large uncertainty in it. But we can compare that, and I have a better figure about this, but we can compare that to climate and also tectonic. And I can do that another time with climate, but in fact, we basically see no relation with climate. However, is a good relationship with tectonics, and tectonics is, for instance, those two lines here, the blue and the black. I have 2 minutes. So the blue is Iberia Europe convergence rate according to Mackie and in 2018. In black, it's one view of the Southern Pyrenees shortening rate according to Gruhl et al. In 2018. As you can see, so basically the blue is the convergence rate between these two plates, Iberia and Eurasia. Okay? So here they go against each other at a rate of less than 1 millimeter per year. Here it decreases a little bit at the end of the Paleogene zero, and then there's a large increase to something about 2 millimeter per year. Okay. At the boundary, why is it at the Paleocene-Eocene boundary? Okay, that's here there's an effect, of course, in nature so abruptly. Okay, it's probably much more smooth. So there is a bias here in our glasses. The glasses we see the evolution of convergence rate are biased by our definition of time in the system. Okay, we have a certain time interval or no detail. Therefore, we go from one time interval to another, and we plot the average rate during that time interval. That gives this very of things. But clearly, this increase in convergence rate is, the increase in topography takes a certain amount of time, perhaps 5 million years, but it takes place after this change in. And then, so here we have a constant convergence rate, then it decreases a little bit, and we don't have the resolution to see if it has any effect in topography. Increases again, not much, in terms of relative rate with respect to the one before, 5 more. And so this seems to have a strong effect on topography growing again here. What I think is really nice is that you stop convergence or nearly stop it. And this has almost no effect on topography. Okay, there is Miguel actually sent me 120 pages paper by Calvé and others that I still haven't read because I can't. But there's still a lot of debate as to how post-orogenic, so this will be the post-orogenic period, as to how the topography of the period after the orogenic time. But clearly this corresponds well to what we discussed previously, that even if top convergence, not so easy to just erode your mountain. Okay. What I wanted to highlight here is that we see we see the signal of topographic growth in response to tectonic. And I think I should stop here, not to go too much overboard, and we'll continue tomorrow with me. So if you have questions, I can take questions, but then you should have a break and start again at 3:15.
Question: the yellow line which says exhumation peaks.
Yes.
What does exactly mean exhumation peaks?
So this is a paper by Whitchurch in which that Alex was in, actually, also Alex Whitaker and the group of Phil Allen. Amy Whitchurch did a compilation of I think mostly appetite and non-fission data, in which you have the ages at which you find most of the exhumation taking place. So that's when most of the grains you find on the field gone to this cooling temperature. And so she finds it's I would not so easy to interpret, but she finds period of increased exhumation, increased. It will be a record of more passing through that boundary and being exhumed, and more erosion taking place, I think, at that time. She finds about 75 or 79,
8, yeah.
78, then 50, you know, climatic optimum, by the way. But sometimes there are coincidences, and that's where time really matters. And 30. It's a paper from, you see, is it? It shouldn't be 2001. It's probably 2010. I think I made a mistake here. I could be wrong, but I think 2010 rather than 2001. And I think there's much more than that. But these periods of exhaustion quite, you know, with the initiation of shortening and mountain building, this period of mountain building and the period of mountain building here.
Okay. Yes, I just was a bit confused if that actually yellow can relate any of the y-axis, but it's just in terms of time.
Sorry, no, there is not.
Uh-huh.
I just it's just symbolic. It's because it's represented as the functions, and so there is no vertical scale. It's just the a peak exhumation. And I also didn't I also don't have information. I didn't synthesize the information on the rates of exhumation.
Okay, thanks.